Okay, in the last class we have discussed some transformations on the independent variable, that is time shifting, time folding and time scaling. We will discuss two important elementary signals in this lecture. One is unit impulse and one is unit step, and they also play a very important role in the analysis of systems. Okay, so we will discuss first these signals in the discrete time, and then we will see their counterparts in the continuous domain, because it is more easy to analyze in discrete as compared to the continuous time. So we first define a discrete time impulse signal. Discrete time impulse. Okay. It is denoted with delta n and is defined as 1 when n is equal to 0, 0 or n not equal to 0. Okay. A very simple function. So what it means that you have a single sample at n is equal to 0, and this is 1. For all other values of n is equal to 1, 2, 3, 4 and so on, or minus 1, minus 2, minus 3, it is 0. Okay, this is what is called as impulse signal, right? And in case if you shift this signal in time, you can have, suppose, delta n minus k. So if it is delta n minus k, it means the impulse signal is shifted in time by k samples to the right. So you will get a impulse at n is equal to k. Okay, so at n is equal to k, the sample value is 1, otherwise it is 0 everywhere. Similarly, for delta n plus k, it will be 1 at n is equal to minus k, else it is 0 everywhere. Okay, and at n is equal to minus k, its amplitude is 1. So you can say that the unit impulse signal has a value is equal to 1 when its argument is 0. Okay, means if it is delta n minus k, when n minus k is equal to 0 means when n is equal to k, at that sample its sample value is 1. Similarly, for delta n plus k, when n plus k is 0, that is when n is equal to minus k, at that sample number its magnitude is 1, otherwise it is 0. Okay, this is a very simple function which is called as unit impulse. Okay, this is unit impulse because its sample value is 1. Otherwise, if you say you have a impulse like this at n is equal to 0, if its sample value is 2, so you can write it as 2 times delta n. Okay, impulse signal. So when it is unit impulse, it means it is simply delta n and the sample value is 1. Okay, now then we have discrete time unit step function, which is defined as un, denoted by un, and it is taken as 1 when n is greater or equal to 0, 0 for n less than 0. So if you plot it, at n is equal to 0 it is 1, at n is equal to 1 it is again 1, at n is equal to 2 it is again 1, at n is equal to 3 it is again 1, and so on. So for n less than 0 it is 0. Okay, this is a unit step function and unit impulse function in discrete time. Now if you see the relation between these two, the relation between the delta n and un, delta n is what? At n is equal to 0 it is simply 1, otherwise it is 0. Un is 1 for n greater than 0, otherwise it is 0. Okay, so how you can recover delta n from un? So the simple way to do this is that if I delay this unit step function by 1 to the right, it will become u of n minus 1. And if you plot u of n minus 1, it will be like this. It will start from 1 now. At n is equal to 0, its value will be 0 because it is shifted by 1 to the right. This is u of n minus 1. Okay. And if you subtract u of n minus 1 from un, all the samples which are beyond n is equal to 1, they will be subtracted, you will get 0. And at n is equal to 0, since it is 1 and this is 0, so 1 minus 0 will be 1. So delta n is simply nothing but it is u of n minus u of n minus 1. This is a simple relation between the impulse signal and the unit step signal. Now if you denote un in terms of delta n, so how you can write it? I can write un in terms of delta n as a running sum of delta m from minus infinity to n. Okay, if you interpret this equation, what it says that in order to find the value of this function un at any time n, you have to use this running sum from infinity to that value of n. So if you first see delta m is an impulse signal which is 1 at m is equal to 0. And this un, which is the unit step function, this is basically the running summation of this unit sample from minus infinity to any value of n. Okay, so it means I have this interval of summation. This is suppose n here, and this is my interval of summation. So what this equation says that if I want to find the value of un at suppose n is equal to this point, so I have to add all this. I have to add this function from all the values of n extending from minus infinity to n. And when you add from minus infinity to n, you will see that there is only one impulse located at m is equal to 0. Rest it is 0 everywhere. So it means your un at this value of n will be nothing but 1. Okay. Similarly, if you take this n here at this point, you have to add this unit sample from minus infinity to this n. Again, in this interval of summation, there is only one impulse at m is equal to 0. As a result, this sum will be again 1. It means for any value of n which is greater than 0, this sum is going to give you a unity value for any value of n. And in case if this sum, if this n is less than 0, so delta m is at m is equal to 0, it is 1. And if the interval of summation is from minus infinity to n, where n is less than 0, okay, what will happen in that case? You are only adding from minus infinity to n, and this n is behind this n m is equal to 0. In that case, this unit impulse which is located at m is equal to 1, this will not come in the summation. So as a result, your sum will be 0 for any value of n which is less than 0. Okay, so for any value of n which is greater than 0, your un will be 1. For any value of n which is less than 0, your u of n will be 0. So you can generate a unit step from unit impulse. You can also rewrite this equation as this. Suppose I change this summation from m is equal to k, where k is equal to n minus m. Okay, in that case, what will be my u of n? It will be delta, your m will become n minus k, and this summation when n is equal to, this is summation with respect to m. Now we are changing it to k. So when your m was n, your k in this equation will become 0. Okay, n minus m, and m is equal to n. So n minus n, it is 0. And here your k will go to, m is minus infinity. So what will be k? So minus n minus minus infinity. So minus minus, it will become plus. So it will go from plus infinity to 0. So or you can write it as delta n minus k from 0 to infinity. Okay, you can also write un in terms of delta n using this equation. And if you interpret this equation, it is what? It is delta n, then delta n minus 1, then delta n minus 2, then delta n minus 3, and so on. And a linear superposition of all the impulses. It means you have one impulse which is located at n is equal to 0, and that is your delta n. Then second pulse, which is located at n is equal to 1, it will be delta n minus 1. Then third pulse at n is equal to 2, which is delta n minus 2, and so on. 0 to infinity. If you add all them together using this equation, you will get a impulse unit steps function un. Okay, otherwise you can also interpret this equation in terms of the running summation like we have done here. And how you can do that? You have un, which is summation of delta n minus k, where k ranges from 0 to infinity. Okay, so this is k. Delta n minus k will be 1 when n is equal to k, otherwise it is 0. And now what is my interval of summation? It is from 0 to infinity. Okay, this is the interval of summation. So as a result, what will happen? When you use this summation, you will get only one sample when n is equal to k. At that time, this signal will be 1. Otherwise, it will be 0. So for any value of n, so suppose you want to find the value of un at n is equal to 1. So it will be 1 minus k. And when you run this summation from k of 0 to infinity, so when k will become 1, at that time it will become delta 0. It means that n is equal to 1, its value is 1, rest of this is 0. As a result, in the summation, you are getting just only one impulse at n is equal to k. So this sum will turn to 1 for any value of n. So at n is equal to 1, it is 1, at n is equal to 2, it is 1, and so on. And if n is less than 0, this pulse will be basically shifted to the left. Okay, and when you sum from 0 to infinity, this pulse will not come into the picture. As a result, for n less than 0, this summation is always 0. Okay, this is how we can relate unit step and unit impulse and discrete time. Now in the continuous time, it is somehow difficult to more understand. So we will use this developed relation. So you have un, we have two relations. Now delta n is nothing but u of n minus u of n minus 1, and u of n, it can be represented either as the running sum of delta m from minus infinity to n, or you can write un as a summation of shifted impulses where k is from 0 to infinity. Now using these three basic equations, we will develop a similar relation in the continuous time. Okay, so you first define unit step function in continuous time ut. U of t is defined as 1 for t greater than 0, 0 for t less than 0. Okay, so if you plot it, this is my unit step function ut. So for t greater than 0, it is 1, for t less than 0, it is 0, and there is a point of discontinuity basically at t is equal to 0. Now from this unit step function, we define the unit impulse function in continuous time, which is delta t. So how you can define delta t? We will use the help of this relation between delta n and un in discrete time. So in the discrete time, delta n, you can see it is the first order difference. Okay, it is un minus u of n. In the continuous time, what will happen? The difference will be replaced with derivative. Okay, in discrete time we have difference equations, in continuous time we have differential equations basically. So the first order difference in the discrete time will be replaced with the first order derivative in the continuous time. So I can denote the impulse function delta t as nothing but differentiation of ut. So unit impulse is defined as the derivative of unit step function. Okay, now this is my ut. If you differentiate it, what you will get? Since it has a point of discontinuity at t is equal to 0, so formally this function is not differentiable. Okay, so in order to find delta t, what we do, we first take a approximation of ut, which we denote as u del t, and in this approximation we assume that this ut function, it goes from 0 to 1 not instantaneously, but it takes some time. That time is del. Okay, so it rises to 1 and then it remains constant. Now if I differentiate it, or from this function, what will be ut? Ut will be nothing but u delta t limit your del approaches to 0. So when this time in which this function rises from 0 to 1, it is close to 0, you will get a very close approximation of unit step function. And this is basically what is a practical unit step function. You cannot have a signal which goes from 0 to 1 directly. It will take some time. So that time may be very less, but this time has to be there. Okay. Now this is the approximation of unit step. And if I find its derivative, I will get a close approximation of delta t. So that I denote with delta del t. Now this function is differentiable. Okay. So between 0 to delta, if you differentiate it, so differentiation gives you nothing but the slope of this line, straight line, and the slope of this is nothing but 1 by delta. It means between 0 to del, the derivative is 1 by del, and beyond del, since it is constant, its derivative is 0. So the derivative of this function will be like this. Okay. So it is a rectangular pulse with a height of 1 by del. Okay. With a width of del, and the area of this is 1. Okay. And from this pulse, if you can get the ideal impulse signal from delta del t when the del approaches to 0. Okay, so if this pulse width del is very small, so that its time, you can say width, has no significance for practical purposes, that will give a close approximation of a ideal impulse signal. It means when you denote a impulse signal delta t in continuous time, we denote like this. At t is equal to 0, we have an arrow and we write here 1. Now you should keep in mind that this 1 is not the magnitude of this pulse as it was in discrete time. This arrow indicates that you have a pulse of very small duration which is concentrated around t is equal to 0, and the area of the pulse is basically 1. Okay, the area of this pulse is 1. not the height is 1. This is the difference between the discrete and the continuous impulse signals. Okay. Now we will try to again develop the relation between the unit step and the impulse signal in continuous time. In discrete time, we have taken it as a running summation. In the continuous time, in place of summation, it will be a running integral. Okay. So in the discrete time, what we have done, we have represented u of n as a summation of a running sum of unit sample from minus infinity to n. In the continuous time, ut will be integration from minus infinity to t del tau d tau. Okay, these are two analogous equations. It means for t greater than 0, this integration should give a value equal to 1, and for t less than 0, this should give a value equal to 0. Okay, and you can again use the same concept. You have delta tau here. Now delta tau is what? It's a unit impulse function concentrated around tau is equal to 0 with a unity area. Okay, this is delta tau. Now to find this function ut for any value of t, we are integrating this pulse from minus infinity to t, so that t can be greater than 0 or it can be less than 0. So if I suppose t is here, it means my interval of integration is from minus infinity to t. In the previous case, it was interval of summation. It will become now interval of integration. So if you want to find the value of this function at this time t, you have to integrate this pulse from minus infinity to t. So as a result, what will happen? You will getting just one pulse located at tau is equal to 0 with unity area. So this entire integration will become nothing but 1 for any value of t which is greater than 0. It may be here also, it may be here also. But if t is less than 0 and your impulse is located at tau is equal to 0, delta tau, and if t is here which is less than 0, your interval of integration will be from minus infinity to this t. Okay, so this unity area pulse will not come in the interval of integration. So for t less than 0, your integration will be simply 0. So this is how you can generate unit step from unit impulse. Similarly, we have another relation here which was delta of n minus k from 0 to infinity. Okay, so using the same concept, using the variable, you can also write this equation in this form. Okay, so for that you have to change the variable. So I suppose take it as, in place of tau, I take it as a tau is equal to, sorry, not tau, I take it as, take tau, change tau to sigma is equal to t minus tau. So my ut will become delta, the tau will be equal to your t minus sigma, and d tau will be minus d sigma from this equation. Okay, and what will be the limits? In this case, your tau was from minus infinity to t. Now when tau is t, your sigma will become 0, and when tau is your minus infinity, your sigma will become again infinity. Okay, so you can convert it from 0 to infinity. This minus sign will go out. You can have sigma t minus del t minus sigma d sigma. So this can be alternate relation to represent unit step in terms of unit impulse. So this equation and this equation, they are almost same. The only difference is here we have a summation, here we have a integration. Okay, Again, if you interpret this equation, now we have a integration of one pulse only, which is located at sigma is equal to tau. This is sigma now, and sigma t minus tau be 1. It is the impulse when t is equal to sigma. This is delta t minus sigma. Otherwise, it is 0. Okay. So for any value of t, you are integrating now from 0 to infinity. So in this integration, you are again getting only one pulse of unit area. So this ut will become 1. For t less than 0, this pulse will not come in the summation because your summation is from 0 to infinity, and this pulse will be for t less than 0 to the left side. As a result, your ut will be 0 for t less than 0. Okay. So this was a very important concept, how you develop the relation between unit step function and unit impulse function. So unit impulse function itself is very important because other functions, they can be written in terms of unit step. Like suppose if I take a function like this, xt, this is put 0, this is 1, this is 1. Okay. How can I represent this function in terms of unit step function? So what we simply do, I first take a unit step function ut, and then I delay this function by 1 to the right. It will become u of t minus 1. Now this is t is equal to 1. And if you subtract u of t minus 1 from ut, you will get nothing but xt. Okay, because for t greater than 1, both are 1. So 1 minus 1, it will be 0. From 0 to 1, this is 1, this is 0. So 1 minus 1, it is 1. So xt is nothing but u of t minus u of t minus 1. Okay. So like this, you can generate any function from unit step. Okay. The rectangular pulses, they can be represented in terms of unit step function only. Okay. Now if I differentiate this function, what you will get? Since xt is u of t minus tau, and we have seen when you differentiate unit step function, you get an impulse function at the point of discontinuity. It means derivative of ut is nothing but delta t at t is equal to 0. So we are getting one impulse at delta t. Then minus u of t minus 1. When you differentiate it, you are getting another pulse at t is equal to 1. But since it is minus, the area will be minus 1. This will be delta t minus 1. Okay. This I have obtained by differentiation of this function. And if you want to recover this function xt from its derivative, you can use again the same concept of running sum. Okay. I can get xt from its differentiation by using this function minus infinity to t. Suppose this function I write as yt, which is derivative of xt. So y tau d tau. Okay. And how you get this? When you integrate this, now your interval of integration is from minus infinity to t. So t can be anywhere. Okay. Suppose I take a t between 0 to 1. So my level of integration is from minus infinity to 1. So for any value of t which is between 0 to 1, when you integrate, you are getting just one pulse which is located at t is equal to 0. So as a result, its value will be 1. So between 0 to 1, you are getting 1. Now when you reach at 1, when t is equal to 1, these both pulses will come in the integration. And since they have equal and opposite area, you will get 0. Integration will be 0. And if you take any t which is beyond 1, so for any t which is greater than 1, these two pulses will always come in the interval of integration. As a result, the net result will be 0. So for t greater than 1, it will always remain at 0. Okay. So this is how you can understand this interval of summation. Now there is a question for you. You have to submit the solution of this question immediately after you see this lecture. Suppose I take a function xt like this. This is 1, then it goes to -1, then again 1. Okay, this is 1, this is -1, this is t is equal to 0, this is t is equal to 1, t is equal to 2, t is equal to 3. Okay, you have to first express this, function in terms of ut only unit step. In the second part, you have to find the derivative of this function. Okay, and in the third part, you have to show that how you can recover xt from its derivative using running integral. Okay, I have explained this concept for you in one example. So you have to apply the same procedure here, and you have to find the solution for this, and you have to scan it and upload it on the Google Classroom. I will share this link for you. Okay, so based on this, your attendance will be counted whether you have seen this lecture or not. Okay, thank you.